Hello students, so in this lecture we are studying about the reasons of the width of spectral lines. That means in any spectral line we see that the peak is not a single peak, it is actually consists of a width. This is how the peak looks like. So what is the reason of getting this sort of width of any spectral line? Now there are three reasons why we get a peak. The first reason is it's called the natural width. The second reason is Doppler effect. And the third reason is there are some external effects. And by external, what we mean is it can be a collision damping, there can be pressure broadening, and then can be Stark effect. So these three mainly come in case of external effects. We will take up one by one. First is the natural width. Now, the natural width in the spectrum lines arise as a result of electron transitions between two energy levels. So, now as you know that the energy levels of the atoms are not discrete, but they have got a certain distribution of energy, they are not discrete, so there are certain energy range in which they are distributed. So let's call this one as delta E, and so this is how the distribution is there. So so whenever an transition taking place from higher energy level to lower energy level, so say this is the ground state and this is the excited state. So whenever a transition is taking place, so there is a probability distribution which is giving the width of the spectral line. Now, a transition between two such levels cannot give an infinitely sharp spectrum because of the Heisenberg's oscillator principle, delta E and delta T. They are equal to H. So when we say delta H, we mean that H delta nu into delta T H. So there is always an uncertainty associated with the frequency of the wavelength. So that uncertainty is again given by 1 by tau, where tau is nothing but the mean life of the atom in a particular state. So height is the lifetime. That means height is the stability of an atom in a particular state, del what will be the change in the wave, the frequency or the wavelength. That means lesser will be the peak width. So it all becomes upon the stability. So it is quite obvious that in the ground state or in metastable states where the atoms are more stable, so we are supposed to get a sharper peak. So this is all about the natural width. The second reason, as mentioned, is the Doppler effect. So in Doppler effect, in the case of gaseous sources such as a discharged lamp, the center of mass of the source is fixed, but the atoms emitting the light have velocities due to thermal agitation. So in case of any gas, the center of mass, all that is fixed, but the atoms emitting light have velocities. Atoms are under thermal agitation. So they are not fixed. They are under certain velocities based upon the temperature, based upon the thermal agitation. Now these velocities provide them a random motion, and so it is giving them a random motion. Which again is causing a broadening of the spectral lines. So this velocity or the vibrations of the atoms, it has got certain frequencies, and it is due to which we are getting a broadening of the spectral line. Now the line width or this frequency distribution is, in the case of Doppler effect, is given as 1.67 0. This is the natural frequency by C divided by 2RT by mu. So now the question is delta nu or the by nu is equal to delta lambda by lambda. So we can say that delta lambda equal to 1.67 lambda 0 by C by 2RT by mu. So this is actually the effective mass or the atomic weight, you can call it. So we can see that the line width will increase. So this corresponds to the line width. So it will increase with rise in temperature. So it is proportional to, so as the temperature increases, similarly this value will also increase. And secondly, if the mass of the atoms, they increase, so this value will decrease. It implies it is the width will increase with temperature, it will decrease with atomic weight. Now the last reason that we have told are the external effects. Line broadening. First is, as we have told, is called collision damping. And the all high at high pressure, the emitted photon is effectively a series of short range independent wave trains. This causes broadening of the spectral line. And the second one is the pressure damping. Now there is a shift of the spectral line to the red. That is, the line is broadened asymmetrically due to pressure. And the last is stark broadening. That means energy levels of a radiating atom are perturbed by stark effect. That means it is the result of electric field, and the result is an average broadening of the spectral line. So these are the three different types of external effects which causes the width of the spectral line.